Hello grade 11s. In this video we're going to be looking at magnetic flux and how to determine the magnitude of a magnetic flux. Now in the previous video I started to mention to you the whole concept of electromagnetic induction, which means that if I would have a coil like this, which we call a solenoid, with quite a number of loops of my conductor around my solenoid. So that is creating my solenoid. Now, the amount of current or the induced EMF, the electromagnetic force, which is also going to determine the strength of your current, is going to be dependent on the magnetic flux. So that means, remember what we said, for me to induce a current here, there has to be a magnet moving. But we know that around this magnet there's magnetic fields. Now those magnetic fields which surrounds my magnet is what's going to go and enter through inside my solenoid. So I'm going to push my magnet inside my solenoid like that, but if I hold it still, no electric current is induced, no EMF. Alright, so we're going to see that it's directly proportional to the change of the what? The magnetic flux. Now what is the magnetic flux? So the magnetic flux, if I can draw it for you like this. Now let's say I have, and in this case, you're going to see the opening area is a circle. So let's say I'm using a circle like this, but of course I'm going to draw it a bit three-dimensional. So let's say my circle lays flat. I've drawn it now flat. That means that when the north pole is approaching of a magnet, there is going to be magnetic field lines entering into, okay, and we know the magnetic field lines is going to change, but let's look at it like this. So it's going to be away from the north towards the south. So there is magnetic field lines entering into this opening of the solenoid, and that strength. Now the closer my field lines, and you know that the field lines is closest at the north pole and at the south pole. So there is my field lines, the density of my magnetic flux is going to be the highest. Now we're going to say that density of my magnetic flux is, we're going to measure that in, we're going to say the density of my magnetic flux, and we're going to use a capital B, and we're going to measure that in Tesla. So they're going to give you a magnet and say the strength of the magnet is, let's say, 4 Tesla, 5 Tesla, whatever. So the strength of the magnet is going to determine the electromagnetic flux density. So how many lines there is going to be. Okay, so it's a weaker magnet, there's going to be fewer lines, so it's not going to be as dense. But something else is also going to determine this flux, this area of magnetism that moves into my solenoid. What else is going to determine that? Yes, of course, this area. If I have a small opening, so only a few lines is going to be able to enter through. If I have a bigger opening, many more lines are going to be able to enter through. So we see that our magnetic flux, and we're going to use the symbol that looks like this, which is basically a feet, but we're going to use that symbol to indicate the magnetic flux. That means, and magnetic flux we're now going to see is going to be directly proportional to what? The strength of the magnet, yes, in Tesla, times the area, the opening of that area. So if my area is a circle, I will have to measure the radius, or they're going to give it to you in meters. So even if it is in centimeters, remember to translate it to meters. So I'm going to work out the area by pi, radius square, to determine the area that the magnetic field lines or the magnetic flux density is going to hit. And that is going to determine the amount of magnetic flux that's actually moving into my solenoid. So if I would have my magnetic lines approaching this opening or that small opening, that's going to be a difference in the magnetic flux. Why? My magnetic flux, by that symbol, equals, yes, the strength of the magnet. So if I'm going to use a stronger magnet with more Teslas, or a weaker magnet with fewer Teslas, that's going to determine, of course, the magnetic flux. But it also is determined by the area where the field lines can enter. Now it could be a square, it's not necessarily round, although most solenoids is actually round, but we could also have it like in a square. And then you're going to work out the area by saying square meters, so it will be meters squared. Alright, so it's going to be determined by the magnetic flux density in Weber times the area that it's going to hit. So that would be meters squared. Now we're going to measure magnetic flux in a Weber. So a Weber is the same, oh, what did I write there? Oh my goodness, sorry. Magnetic flux density, we're going to measure in Tesla times square meters. Okay, so a Tesla square meter equals 1 Weber. So we're going to measure magnetic flux in Weber. But something else is going to play a huge role. Is those magnetic lines, is it coming straight in? Or is the magnet maybe moved to the side and now my magnetic lines are going to enter my opening but with an angle? Yes, of course that's going to determine the magnetic flux. So we have to bring that in consideration. So what are we going to do? We have to get the component of those lines towards the what? The normal. And guys, here is the big problem. I always see that my kids get confused here. So which is the angle? Now the angle, the formula is going to be cos theta. Because we want the angle between my lines and the what? The normal. Now what again is the normal? If I have my magnetic opening here, this is my coil, my solenoid, and I've got my opening there. And this is my area, that circle, okay? Then my normal, like we've already learned that with forces, is going to be a line, of course, that I can't see, a line that is perpendicular to the area with a 90-degree angle. And then we're going to determine that cos theta, the angle, is the angle between the normal and the direction of the magnetic field lines. So if the magnetic field lines are hitting my area with an angle like this, I'm not going to look at the angle to the area. I'm going to look at the angle that it forms to the normal. So when they say magnetic field lines are hitting the area with a 90-degree angle to the area, what is cos going to be? Now remember, if it hits with a 90-degree angle, there's going to be the most field lines going through. So my magnetic flux is going to be the biggest. The highest magnitude that I can have is if it falls perpendicular to the area. But remember, I'm not looking at that towards the area, I'm looking at the angle with what? With the normal. So if this is my field lines, and this is my normal. What is the angle between the two? 0 degrees. And what is cos 0? It's 1. So you're going to always use here. So if I can show that to you again, let me use maybe a different pen color. So there is my area. That is my normal. That's just the line. Of course, I can't see it, but I know it's 90 degrees to the area. And if I then have my magnetic field lines coming with an angle, I'm not going to measure the angle towards the area. I'm going to measure the angle towards the norm. Now, if that is going to be 90 degrees to the area, perpendicular, so my field lines hits the area 90 degrees, perpendicular, full on, then it's going to be cos 0 degrees. And what is cos 0 degrees? 1. Now let me change this, and I'm going to show you what is going to happen if my field lines is going to go at an angle of 90 degrees or of 0 degrees. Okay, so now my field lines comes across like this. How many field lines are going to actually enter into my solenoid? 0, nothing. Okay, but what is the angle between my field lines and my normal? 90 degrees. And what is cos 90? 0. So let's come back to that. So let's say this is again my area. Now my field lines is going to go across like this. But here is my normal line. Okay? So now I'm going to say between the direction of my magnetic fields and the normal is a 90 degree angle. So cos 90 degrees, and if I put that into my calculator, you're going to see cos 90 degrees, say, times 0. So whatever this is going to be times 0. So the magnetic flux is going to be 0 Weber. No electromagnetism induced. No current induced. So it has to hit either full on or with an angle. And how do I measure the angle? Okay, so let's come back to the formula. So they're going to now be able to say to me, all right, determine the magnetic flux. What's my formula? There's my magnetic flux. And they say a magnet with a strength of, let's say, 2 Tesla, so that's going to be my magnetic flux density, times my area of the solenoid, times cos theta. So that is the formula that I'm going to use. So that is, let's say, the magnet that they're using is a strength of 4 Tesla times, and they tell me it's a square of, let's say, 2 meters by 2 meters. So that's going to be 2 times 2 is 4 square meters. And let's say they say it's the angle at which the magnetic field lines hit is 90 degrees to the area. That means it's going to be cos 0 degrees. Why 0? Because if it comes full on, the angle between my lines and the normal is 0 degrees. So 4 times 4, so that gives me 16 Weber. So that would be my magnetic flux. Now, what really is important for us, what we're going to really use in Faraday's law, is not the magnetic flux, because, like we said before, I can have that magnet and it's got a magnetic flux, which is now in there, because of the magnetic strength or magnetic flux density, times the area, and I hold it still there. Nothing is going to happen. So what is important? That magnetic flux has to change. And it is the rate at which I am going to change the magnetic flux that's going to determine the magnitude of my EMF. So if I want to have a high EMF of I don't know how many volts, I have to change the magnetic flux. Therefore, we're going to have to work out what is the change in magnetic flux. And to determine that, we're going to say the final magnetic flux minus the initial magnetic flux. So there should be some kind of a change. So it could be, of course, the area is not so easy to change the area of the opening of my solenoid so quickly. Alright, so the area is most of the time going to stay the same. But they could say that the magnetic flux density is changing from, let's say, 4 Tesla to 2 Tesla, depending on the density of your field lines. And the moment there's a change, I'm going to first say what was the magnetic field, that was my initial magnetic flux, what is my final magnetic flux, and I'm going to work that out. Or they could say, how they can also get a change, is to say the magnetic flux comes with an angle of 30 degrees and it changes to 0 degrees. So there's going to be a change then in cos 30 degrees minus BA cos 0 degrees. So there has to be a change. What they can also do is that says that there's a magnetic flux moving in from nowhere. So it's coming from very far away. Then I can say, oh, my original magnetic flux equals 0. There was nothing. And the next moment it comes in full force with what? With the strength of your magnetic flux density times the area of your opening of your solenoid times cos the angle with which it. Then it's going to be 0 or final minus 0. Or it could be that there was a magnetic flux and you pull it away. So you take the magnet out and away. So it becomes 0. Then you will substitute your final magnetic flux as 0 minus your original flux, which was inside the solenoid and which you can then work out with BA cos theta. Okay, so this is just the introduction today to determine the electromagnetic flux. And we're going to measure magnetic flux in Weber, and 1 Weber we just saw now equals a Tesla square meter. But guys, this is new work, so I hope it's not too confusing. Remember, as you start to work with these formulas, it's going to become more familiar, and by next year this time when you're busy with your matric, you're going to say, oh no, that was easy peasy, I can do that. I remember what is magnetic flux and that is easy to determine. Alright, but believe in yourself, you can do this.